Hello everyone and welcome to another video. Today I'd like to look at deriving Rodrigues rotation formula. I first ran into this in Stephen and Lewis's 2003 textbook entitled Aircraft Control and Simulation 2nd edition. In this, they use a different name of Goldstein's rotation of a vector formula in reference to Herbert Goldstein's 1980s textbook entitled Classical Mechanics 2nd edition. Actually, this was originally derived almost 150 years prior to that in 1840 by French mathematician Olinde Rodrigues, from which it derives its name. So if you want additional references on this, then Rodrigues rotation formula is definitely the more popular set of keywords to type in your favorite search engine. Despite this, I'm so used to Goldstein's approach that I'm going to follow his derivation, which is slightly different, but we end up in the exact same place in the end. Just out of habit, I'm going to continue referring to this as Goldstein's rotation of a vector formula, but it might be more beneficial for you if every time you hear me say the name Goldstein, just switch it in your head with the name Rodrigues. Regardless of the history, we're going to see that this is a formula which is going to allow us to rotate a vector about another arbitrary axis of rotation to arrive at a new vector. Now, this has applications in fields such as orbital mechanics, computer graphics, and rigid body dynamics. The derivation isn't that bad, so let's just jump into it. So I always think it's easiest to look at a concrete example here. So to help us understand what this formula is and what it does here, I made a couple of props that might help us here. So here's my prop here that represents, just an arbitrary vector. So it's got a start and it's got an end here denoted by this blue cap here. It's actually the end of a dry erase marker here. We'll take a look at that, why that is in a second. And now what I want to be able to do is to take this vector. Let's denote this vector here as u. Okay. So the u vector here, maybe it might help us if we label this thing. So I'm going to label this as u bar here. So this is my original vector u bar. And it's got an origin here. Maybe let's call that the origin point. Let's call the origin point O here. Okay, whoops, sorry, I don't know if that's a little difficult to see there in the camera, right? And the tip of it is point capital V here, right? So here's my vector. You can also denote the vector u as going from O to V here, okay? Now what I want to do is I want to rotate this vector about an arbitrary axis. So let me go ahead and grab another vector. Let's call this n here, right? So maybe what I've got is I've got myself a little notation here. So this is my vector n, and n is going to start at the same location as O. So actually to help us hold all these together here, I've got this little coupler here. That might make this a little bit easier to understand here. Okay, so here's the picture. I apologize. These labels are probably not going to work out very well here, but here's my 3D picture here, right? So I've got this axis of rotation n bar here, right? So this is going to be a unit vector of length 1 here, which simply denotes the axis of rotation here. And now what I want to do is we are going to rotate this vector u about the axis n bar, but I'm going to do it in a left-hand sense here. So what that means here is your typical right-hand rule, right? So here's my right hand, right? You point your thumb here in the direction of the axis of rotation, and the way your fingers curl denote a positive angle deflection. So this is usually considered a positive deflection in that direction, but in this formulation, I want to look at, well, actually Goldstein and Stevens and Lewis want to look at a left-handed rotation. All that means is we're going to go in the opposite direction. So a positive deflection here, or a positive rotation about the axis n here, is actually in this direction of a left hand. So I'm going to take my left thumb, point it in the direction of where I want to go, and I'm going to curl my fingers here. So for example, this would be a positive 90-degree rotation here. Okay, so all we're doing here is we're going to take the vector u, we are going to rotate it about this vector n through some angle, let's call the angle mu. Okay, so that's all that's going on, is we're just going to be rotating around this axis n here. A couple of things to maybe note here. One other thing that we may want to do right now is, if you look at this long enough, you'll see that the angle between n and u, it's constant, right? I mean, it's fixed here, right? So you see as you rotate this around, let's denote this angle here as phi. So again, I apologize, this is going to get a little bit complicated here, but here we go. Now I've got this angle phi here between the axis of rotation n and the vector u here. Oh wait, gosh, sorry, I grabbed the completely wrong label. Sorry, I grabbed the the v, sorry guys, the end of vector u should go from O to U here, right? Because what we're trying to do here is, again, let's say I'm going to rotate this around the vector n, okay? And I'm going to now end up with a new vector. Let's call this new vector v, okay? And this new vector v, it has the exact same origin that u did, namely it starts here at point O, and now let's call this last ending point v, okay? So again, I apologize, this is a little bit complicated with all of these sticky labels here, so maybe what would be easier here is, let's just take a couple of these off, let's take all these labels off, and just look at this and think about what this is going to do. So again, you've got the vector u, you've got your axis of rotation n here, and all I'm going to do is I'm going to rotate around. And in fact, maybe let me move over here and we'll get two camera angles so you can see what's going on here, right? So the main camera angle is going to be from the side, and then I'll show a picture-in-picture of a second camera angle which is looking straight onto this as we rotate around. So again, you've got your vector u. I am now going to rotate it through a left-hand rotation about the axis n, and all this does is it rotates around. So if you look at this long enough, you can see that, you know what? The tip of the vector u, doesn't that go ahead and trace out a perfect circle here? And the plane of that circle is actually normal to the vector n, right? To actually maybe convince yourself of that a little bit more, maybe let's align this with the board here, and actually let's extend this unit vector n so it goes to the plane of this circle we were talking about. So in other words, let me see, I've got another piece of pipe here that we can use to extend the vector n. So now this is a vector that it's in the same direction as the unit vector n, but it goes to the plane of this circle here. And to convince yourself of that, let's go ahead and take the cap off of this. And maybe what I'm going to do is I'm going to align this vector n to be normal to this whiteboard here, right? So if it's sitting here something like this, right? And now all I'm going to do is I'm going to rotate through a left-handed rotation about this vector n. So that means I'm going to go in this direction here, right? So you see, as this thing rotates around through a left-handed rotation, the tip of the vector is going to trace out this perfect circle. And again, I guess I didn't do that entirely perfectly here, but I think everyone gets the picture of what's going on. So this is the geometry of the problem here, right? So with that in mind, I hope I didn't confuse everyone too much with all of these labels, but now you've got an idea of the mechanics of what's going on. Let me pause the camera, put my props down, and we'll come back and clean up this diagram and label all of these points exactly, okay? All right, so it might be helpful to go ahead and draw sort of an isometric view of all of these vectors and angles. So again, we said we started out here with this point O, which was the origin here, or the starting point of all these vectors. And again, we said we started with this vector u, right? And it came out here to this other point u, and I'm going to try to draw again an isometric viewpoint. Maybe I'll do this in blue just to sort of match up with the other picture down here. Okay, so we said we had the vector u, we also had a vector n, right? Let me draw this maybe in red. This was our axis of rotation here. So this is the vector n hat, right? That was our unit vector here. And the idea was that we rotate this vector u, and it's going to trace out this circle in a left-handed sense so that we end up now with a vector v, right? So this was our vector v in green here. And the top point up here was point v, okay? Okay, so then we said, all right, you can go ahead and extend this unit vector n, and it should get pretty much to the center of this circle here, right? So if you look at this long enough here, we actually have a couple of angles here, right? So there should be this point here where the unit vector extends and pierces this plane here. Let's call this point big N. Maybe I'll do this in red. Okay, So it's the extension of the little n bar goes to this point n here. Okay, and then this is basically the center of the circle. So down here in this picture, maybe just so that we're all on the same page here, maybe we should draw all of them, because remember this was the picture where we are looking directly down the direction of n, right? So maybe we should draw n here. N is going to be into the board, right? So here's n bar, right? And this point where it pierces here is point big N, right? Okay, and now what we said here is that there's a couple of angles we can draw here. So maybe let's do this. Maybe let's do everything in the plane in blue may be helpful, okay? So there's this distance, right, where I can go from here to kind of over here, right? We said this point out here was point U, right? And then this thing was swept through and rotated till we end up with this other arbitrary, not arbitrary, but it's another point on the circle here of point V, which we kind of had in green. Oops, maybe I should draw this in black to be consistent. Okay, here is point U. Okay, great. So I think this is looking pretty good here. Maybe I should have drawn this angle. Right? So I think we make a couple of notes here. Well, we can see that the angle between this red dashed line and both of these blue dashed lines, those should be right angles here, right? So this should be a right angle, and this should be a right angle. Right? There's two right angles because it's normal to the board here, right? Okay, so let me see here. I think that's pretty good. And then here's this angle we're interested in, mu. It's this angle here, right? So this is a positive mu, right? Because again, it's a left-handed rotation. So it's opposite of a right-handed rotation here. So again, let's draw it in both pictures here so this makes sense. So here's positive mu, right? Okay, great. I think we've got most of the stuff we need. We have the point O, U, V, and one more actually that's interesting. Let's come here to this plane because I think this is the easiest to visualize this. If we drop a line straight down here so that there's a right angle here, let's call the point where it intersects right here, let's call this point W. Okay, so again, this is going to get a little bit complicated here because again, blue is everything in the plane here. So again, these should be a right angle, and here's the point W. Okay. All right. Oh, lastly, I think the only other thing we didn't mention was this angle phi here. So the angle phi was between the unit vector n and the original vector u here. So this is our angle phi. It shows up here in this picture. You can't really see it in this picture because it's in the plane here. Okay. All right, I think that's most of the items we're going to need for our derivation here. So let's keep these two pictures in mind. Again, here's our isometric view. Here's our view directly looking down the axis of rotation n here. So let's make a couple of notes here. So things to note. Okay, again, just so we're all on the same page here. So n here is a unit vector, right? And furthermore, it's in the direction, we could say in the direction of O to N, right? You can kind of see that from that picture. So it's in the direction, let's call this vector ON bar. Well, maybe we'll point in that way, right? So in other words, we could write N, it's just the length, or it's the vector ON normalized by its length here, right? Because it's a unit vector here, okay? So that's one thing we need to note. Again, let's make a note here that mu is a left-handed rotation, okay? The other thing we can note here is that phi is constant, right? It doesn't change with mu as we rotate around. This angle between the axis of rotation and the vector u is constant all the time because, like as we saw in our diagram over here, this angle is maintained by this bracket, this white bracket here, right? So as we rotate about this axis here, the angle between these two vectors is always the same. Okay. All right. Great. So all right, I think we've got all that. So what we're looking for right now here is the goal of Goldstein's rotation of a vector formula here is to find a function to describe v as a function of u, n, and mu here, right? So in other words, if you know the original vector here, right, you know the axis of rotation and you know how much you rotate through, I want to know where this new vector v is, right, or how to describe that here, right? So I'm looking for v is equal to something here, right? So if you look at this just from a vector mechanics perspective, I think you'll agree that let's look at where is v. V is the green vector, right? You see that I can get to the green vector from here. If I go from O to N, right, that gets me to the center of this circle here, right? And then what I need to do here is I can go from N to W, I can go over here, and then I can go from W to V to get up to there. So in other words, I can write V here. This is the same thing from a vector perspective. This is ON plus NW plus WV, right? Okay, this is great. So all I need to do now is let's come up with expressions for each one of these three subvectors, and that will give me the overall vector of v that I'm looking for here, right? Okay, so that's great. Let's start with each component here. So let's go ahead and start with finding how to describe the vector ON, okay? So where is ON? ON is this red dashed line here that we saw, okay? So if you look at this here, that's actually not that bad, because if you look at the geometry right here, vector ON, that's just a projection of u onto the vector n bar here, right? So it's a vector projection. So in other words, what we can write down is we can say that ON, well, that's nothing more than the vector projection of u, the original vector, onto the axis of rotation n hat. Right? Now, if you remember from your vector calculus how you get a vector projection here, right? That's just the inner product of u and n, right? All over the norm of n squared times n here, right? Okay, this is awesome, because if you look at this, we were going to make a note here that what the heck is norm of n, right? Well, we said earlier that n, it's a unit vector here, right? So this thing's length is 1, right? So the norm of n is 1, so great. This denominator just becomes 1, and we actually come up with a really simple expression here for ON. ON is just going to be the inner product here of u n dot n. Great, box this up. Let's call this thing maybe equation 1. We'll come back and use them in a second. So that's great. We already found the first one. So ON, done. Okay, let's move on to how about NW here, right? Maybe let me move this over here so we can keep it. I'll erase all that. So again, we said that V, this is just ON plus NW plus WV. Right? That was the vector sum. All right, so let's go ahead and erase some of this. And we will keep going on with finding the other expressions here, okay? So we got ON, so now we need to go ahead and find an expression here for NW, right? Is that the next one? NW. Where is that vector? So here's NW. NW is from here to here, right? Okay, so actually this picture is pretty helpful to use here, right? Because we can see here that let's do the same thing we did earlier with our vector projection here. So if you look at this, here's the vector NW. So it's this little section right here. Maybe we should, maybe I'll kind of draw this in green so we can kind of see the vector we're talking about here, right? Here's the vector NW in green, right? Okay, so if you look at this, this isn't so bad, because this is actually, it's the vector projection of NV onto NU, right? That's one way we could describe this, right? So we could say here that NW is the vector projection of NV onto the vector NU here, NU, right? Okay, great. So let's go ahead and just, again, use our definition of vector projection here, and we can write that, all right, this is, we're actually use our other description here, talking about the cosine of the angle between them here. So we can say this is magnitude of NV times cosine of mu all over magnitude of NU dotted with, or times NU, right? So this would be a multiply. Right, yeah, because it's all scalar, and here's the direction here, right? Okay, great. Let's ask ourselves, what is the magnitude of NV and the magnitude of NU here? So if you look at this, magnitude of NV, this is basically the radius of this circle here, right? And what is NU? The magnitude of NU. NU is, again, it's the radius of the circle here. So we can make a quick note here. So we can say that, note, right, magnitude of NV is equal to the magnitude of NU here, right? It's basically both of these are equal to the radius of circle, right? Okay, so these cancel out, right? Okay, so we end up with, let's write this down. This cleans up a little bit. We get cosine of mu times multiplied by NU. Okay, all right, so let's look at this vector NU here. Where is NU? NU is NU here, right? Or in this picture, here's NU. So actually, another thing that we could write here is we could also note here, hey, you know what? NU, this vector, this is the same thing as the vector U, right? So here's the vector U, here's NU, so it's actually U minus this leg right here, right? Which is ON, right? So now let me just write this down, right? All right, maybe you want to pause the video here and convince yourself that this is true, but if you consider the triangle, right, ONU, you'll basically see that this is just a vector combination here, right? Okay, great. So if that's true, let's go ahead and plug that in here. And we end up with, let's see, NW, right? An expression for this vector component NW is cosine of mu times U minus ON, right? Okay, now let's look at ON here, okay? So let's save this here for a second here, and we're gonna make a note here that we can write that we can say that the vector ON, right? Where's our vector ON? Let's look at our picture here. ON, that's this dashed red line here, right? And that is the same thing as the vector projection of what? It's a vector projection of U, this vector here, onto N bar here, right? And actually, wait a second, didn't we already? Sorry, we just did that. Oh yeah, actually, sorry, this was what we did. So we did this earlier, right? When we were solving for ON, actually, yeah, we already have that, right? We already said that ON was the inner product of U and N onto N here, right? That's what we just did earlier, okay? So this was from equation 1 that we just had, okay? So now I can substitute this into here, okay? So take this expression, put it into ON, and we end up with basically our final expression here. NW is going to be cosine of mu times U minus inner product of U and N times N. I think that's N parentheses. Great, okay, box this guy up, right? Let's call this one, what did I label this thing as? Did I? Yeah, that's right here. Okay, so I called this one equation 3 here in my notes. Okay, so great, that gets us NW, so here we go, we're done with that. Okay, all right, so the last one we got to get here is we need to get the vector WV here, right? So if we're going from here to here, great. So let's go ahead and erase the board. Do that now. Okay, so now the last one we're looking at here is we want to find our vector WV. Okay? All right. So let's look at this vector WV. So here it is. Maybe let's do it, I will do it in, how about solid red? Here, how about? So here's the vector we're looking at here. This one is what we're looking for. This is WV. That's what we're looking for. It's this vector. And we notice here that this vector is actually in the plane of this circle here, right? So, all right. So let's write that down here. So this vector that we're looking for, this WV, so this is in the plane defined by NUV, right? So here's NUV, that defines the plane of this board, and this is where that vector lives here, right? And actually, we can also note here that this is perpendicular. This plane that we just defined here is actually perpendicular to this other plane of ONU here, right? So, so we can also write the other note here that we can say is plane NUV is perpendicular to plane ONU. Right, and again, I think this picture is the easiest one to see it from, right? You can clearly see that because there's two right angles here, by construction, ONU is perpendicular to NUV, right? Okay, so let's see here. So the direction here, if we think about this long enough, of this vector here, of direction of WV here, we can actually get that from the cross product of two vectors here, right? So we can take the cross product of U and let me see, and N, right? And that will actually give us the direction here. So if we think about this here, U is in the direction of the, well, it's not exactly in the plane of the board, but it's mostly in that direction here, right? And N is directly into the board here, right? So the cross product according to our, sorry, I probably can't see that from the camera here, right? So my index finger is in the vector of U, right? Going out here is point O here, right? Maybe we should line up like this. So this is point O. So my index finger points towards point U. That's in the vector U, and then the vector N bar here, right, is actually in the direction of my middle fingers. So my thumb gives me the cross product direction, which is exactly in the direction we want here for WV here, right? So let's make a note here that the direction of WV is given by cross product of U and N. So in other words, let's denote this direction maybe as D here. So D is the direction, then maybe we'll draw it like such. Here's the direction D, right? And by using this observation that they are perpendicular planes here, right, we can say that, oh, right, this direction D here, this is just given by U crossed N here. Okay. Oh, actually, no, I'm sorry. Let's not call this D yet. D is actually, I want this to be a unit vector here. So let's just say the direction here. Direction of WV here, right, is given by U cross N. If you remember the definition of the cross product here, right, so the cross product is, you can also write this as magnitude of U times magnitude of N times sine of the angle between them here, right? Now, the angle between U and N, if you remember earlier, that's this angle phi we said earlier, which is constant, right? This is the angle between U and N, right? So great, this is this, and then we have to give this thing a direction here. Let's call this direction a unit vector D. Let's call this here, like that. There we go. So D here, this is the unit vector in direction WV here, right, that we want. So actually, let's just solve this thing for D here. So in other words, I'm going to isolate D, I'll move this junk to the other side here. So we end up here with the expression we're looking for here. So the unit vector in the direction of WV that I'm looking for, this little D here, this is just going to be U crossed with N divided by magnitude of U times magnitude of N times sine of phi. Okay, now let's make another simplification. If you recall, right, what was the deal with N magnitude? That's a unit vector, so this magnitude is 1. So this guy goes away here, and we end up with our final expression here for D, which we are going to box up and save, and we'll use this for later. So this can be U crossed with N all over magnitude U times sine of phi. Okay, maybe I'm going to call this equation 5 in my notes here, right? Okay, great. Maybe let's, again, box him up. We will use him in a second. And let's go over here. Maybe let me erase some of this so we have a little bit of space here. We don't have to get rid of everything. Actually, tell you what, let's get rid of everything except our result here, right? Okay, we're still here trying to find W, V. Okay, so now let's go ahead and examine the triangle WVN. Okay, so if we look at this triangle here, where is this? WVN. If you look at this, this is actually a right triangle here, right? Here's the right angle here, with the hypotenuse of NV here, right? Or magnitude of NV. It's basically the radius of this circle here, right? So examine triangle over W. We realize this is a right triangle with hypotenuse magnitude NV, right? So therefore this length here, right, shouldn't I just be able to get that as what? It's hypotenuse times, what is that, sine of mu here, right? So in other words, I can write, so what do we end up with? Magnitude of WV, right, is the hypotenuse, which is magnitude of NV, times sine of mu. Right? Okay. Okay, so maybe let me call this equation 6 here. We're going to use it in a second. Okay, now let's examine another triangle here. So how about, well, do the same thing here. So examine triangle ONU, right? So let's look in this picture. ONU, we see, is another right triangle with hypotenuse magnitude of u here, right? So what we can do here is I can find this length here of one of the sides of this right triangle by just relating it to phi here, right? So in other words, what I can say is I can say magnitude of NU, right, is the hypotenuse, which was magnitude u here, times what? Sine, yeah, sine of phi, right? Opposite of that one, times sine phi, right? I think everyone would agree. Okay, and I gotta be careful my handwriting doesn't get us in trouble. This is NU, right? I don't want this to be to make it look like a V. I better make sure that that's really curvy, right? Okay, now what we can do here is, if you remember, what is NU? NU is this distance here, or this distance. It's the radius of this circle here that we've got here, right? So let's go ahead and make a note here that magnitude of NU is equal to magnitude of what? Of NV, right? Both those two things are the same thing. It's the magnitude of the circle here, right? So I could write this thing as magnitude of NV is equal to magnitude of u sine phi. Okay? Okay, so maybe let's call this thing equation 7 here. And now if you think about this long enough, why don't I go ahead and substitute in equation 7 into 6 here, right, for this expression here. So let me write that down. So let's go ahead, maybe I'll do it over here. So let's go ahead and say sub equation 7 into equation 6 here, right? And we end up with, okay, magnitude of WV, right, is equal to magnitude of u sine phi sine mu, right? So this is the length of the vector that we're interested in. Remember, we're trying to find this vector WV. So here's the length, right? Maybe I'll box this thing up right now. Call this thing equation 8. Here's the length, here's the direction here, right? So the overall vector here, right, is WV. It's just the magnitude times the direction. So here's the magnitude. Magnitude u sine phi sine mu times the direction times this thing over here, right, which was u crossed n all over magnitude u sine phi. Great, so let's see, sine phi's cancel out here, and let me see, do we actually have other stuff that helps? Oh yeah, this cancels, right? Magnitude u cancels with magnitude u. So actually this comes out to be pretty simple here. So WV is just going to be sine of mu times the quantity u crossed n. Great, box this up. Let's call this one equation 9. And I think we're done here, right? So now we got the 3 of these things. So putting them all together, let's go ahead and now write down Goldstein's rotation of a vector formula. So overall, at the end of the day, what we end up with here is we are basically going to use, we said what? V was going to be ON plus NW plus WV. Okay, so I think this here was our what we called equation 1, which was inner product of UN times N plus this vector, which I think we said was equation 3. So this is going to be cosine of mu times a quantity U minus inner product UN N, like this, plus WV, which we just got as our equation 9 here, right? So this is going to be sine of mu times U cross N. Great, so this is exactly what we want, right? Everything on the left-hand side we know. We know the original vector u, we know the axis of rotation n by this unit vector, and we know the left-handed angle mu, which we're going to rotate through. So here's the whole thing. If you'd like to, you can distribute this cosine mu through and basically do a little bit of algebraic manipulations. So this is a little bit boring, so maybe I'm just going to write dot, dot, dot here, and let's just say the next here is boring algebra. But you can rearrange these terms and get this thing to look like the formula that you'll find here in Stevenson-Lewis or in the Goldstein text here, if we could find the second edition here. This is 1 minus cosine of mu times the inner product of u n times n here, plus cosine of mu times u minus sine of mu n crossed u. Yeah, you can see this minus sign popped up because originally we had u crossed n here, and now if you just flip the order of the cross product, it'll pop out a minus sign here. But anyway here, this is what we're looking for here, and in this case here, right, u is the original vector, right? N is our unit vector describing the axis of rotation, and mu is our left-handed rotation. Right? I think that's it. And then u is, or sorry, excuse me, v is going to be the resulting new vector. So let's box this up because this is basically Goldstein's rotation of a vector formula here, which is very, very helpful for rotating vectors about an arbitrary axis here. So tell you what, let's go run over to Matlab and actually simulate this just so we can check to make sure this looks reasonable in simulation. We'll just basically implement this. We'll give it an arbitrary vector u, an arbitrary axis of rotation n, and just sweep mu through 0 to 2 pi just to see what does this look like here. And again, what hopefully ends up happening is that we have a situation which looks exactly like the picture, the demonstration we had earlier, right? So we're going to pick some vector u, we're going to pick some other axis of rotation n, and we're going to now sweep it through a left-handed system and watch the vector spin around here, right? Okay, so let's go over to Matlab and see if we can make that happen.
Alright, so I've just got a very quick Matlab script that should hopefully illustrate this rotation. So you got our normal clear CLC close all, and then we're just going to pick an arbitrary axis of rotation n here. So notice here that, remember, the formulation requires that n has to be a unit vector, so I'm just going to normalize here. It's already a unit vector here, but we're going to see in a second that if I want to change it to be something other than just the x-axis, we totally can do that, but I need to make sure that n is a unit vector. Now, u, the original vector, does not need to be a unit vector. It can be pointing in any direction, right? And we're just going to rotate this vector u around the vector n here, right? So all I'm doing next is let's define a bunch of values for mu. So I'm just going to go from 0 to 2 pi in 50 steps here. And now all I'm going to do in this for loop down here is just start a figure and just start going through and stepping through different mu's and rotating the vector u through all these angles here. So I'll just pull off the current mu that I'm interested in and then just apply Goldstein's rotation of a vector formula that we just derived on the board to get my new vector v. And then all I'm going to do here is I'm going to plot u, the original vector, as a red line. So hopefully that's not going to move. I'm also going to draw n as a green line, which is also not going to move. But when we draw the vector v as just a blue line, we should see this rotate around the vector n here, right? That's pretty much it. I'll throw a couple of labels on here so we can see what's going on, and I'll just pick a viewpoint and make the axis large enough so this movie doesn't change as we're going along. So tell you what, let me put a breakpoint in here at the draw now section, and we'll run to this. And let me pull the figure in over here, and maybe let's dock the figure so we can see what's going on. Maybe I'll make this a little bit bigger so we get a little bit more real estate. So as you can see right here, the right now for mu equals 0, both the red and the blue line are on top of each other because we haven't rotated anything around the vector n. So as you can see, the n vector, the way we defined it earlier, it's just around the x-axis. So we should see this blue line start rotating around the green line in a left-handed sense. So let me take off the breakpoint here and we'll just continue running, and there you go. You see that it's going around in this left-handed sense. I know the perspective given this isometric view is a little bit odd here, so tell you what, let's go change the viewpoint here to maybe 90, 0. So we're looking straight down the x-axis here. So in other words, this vector n is going to kind of be poking us in the eye. We're going to be looking straight into the tip of this. So if I rerun this script here, actually tell you what, let me see, I actually need to pull I need to pull this over here. There we go. Okay, so you can see, again, we're looking at it head on, and you see the rotation as this thing goes around, and yeah, everything looks beautiful. Let's just show that this still works here if you don't have a unit vector. I'll change the viewpoint, or I'm sorry, if you don't have something that's nice and aligned with the x-axis, right? N can be something completely arbitrary. So for example, let me just comment out this one, and maybe I'll make some random n vector that's pointing off in some odd direction. Again, we'll just make sure we normalize it so it's a unit vector here. And again, rerun this thing. Let me pull it over, and here you kind of go. You see here's the n vector here. It's pointing off in some odd direction here, and this perspective makes it a little bit screwy, but I think you can kind of see what's going on, that we end up getting this the original vector u being rotated around the vector n. So this shows how this is going to be very useful in the future.
Okay, so that was great. I think we showed now why this Goldstein's rotation of a vector formula is helpful, because it's going to allow us to take some vector u, rotate it about some vector n, and generate a new vector. So I hope this was interesting here. Please join us for our next video where we're actually going to apply this directly to see how do vectors change from different perspectives. We're going to see that this leads to a discussion of Coriolis, or the equation of Coriolis, and further along down the line we're going to be able to use some of these tools that we built up when we want to look at velocity and acceleration in rotating frames. So with that being said, I hope you enjoyed the video. If so, please subscribe to the channel, because we're going to be having many other videos on vector dynamics, engineering, and equations of motion coming up in the future. So I hope to catch you at one of those future videos. Bye.